तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in today's class we shall continue our discussion on I squared L, okay, and just to recollect what we were doing last class, okay, we had drawn the I squared L structure, basic structure of an I squared L cell, which consists of a PNP and an NPN transistor, okay. The NPN transistor is of course a multi-collector transistor, and here you have the PNP which acts as a current source. So, you have the supply voltage here and this is the resistance, okay. So, this is the injector point, this is the so called injector point from which current is injected into the circuit, and you have a PNP which acts as a current source, and this current which flows, the collector of the PNP transistor either flows into the base of this NPN transistor, turning it on or making it go to saturation, or if this input is low, it is going to flow out into the input point, okay. So, this is the input point, and in which case this particular transistor is going to be cut off. So, that this transistor is either in saturation or in cutoff. So, this is a saturated logic, okay. The transistor goes to saturation. We had also drawn the cross sectional view of this particular gate, this particular cell, okay. So, you have the structure which we had drawn is like this. You have an N plus substrate, you have the N plus guard ring. So, we shall today's class we shall discuss in detail this particular structure. So, you have the injector, then the base, and you have the collectors, all right. So, P, this is also P. So, this is the injector point terminal, this is the base or input terminal, and these are the collector terminals, and the ground is at the bottom, okay. The ground terminal is at the bottom. So, you have the injector terminal, this is the input or the base terminal, and you have the collector terminals, in this case 2, but you can have more than 2 collector terminals, okay. It is possible to have more than 2 also, okay. Now, the next thing, so this is what we did last class. We shall go ahead with our discussion, and so today's class what we shall do is we shall do study a little bit about the technology, okay, aspects of I squared L, that is how this is realized, okay, because this is very important especially in the case of I squared L, because most of the advantages of I squared L, as you see it, we discussed the merged transistor structure, okay, as well as most of the drawbacks or problems associated with I squared L is associated with this particular structure, okay, because of because the transistors have been merged, okay, you have a particular structure. So, one really has to understand why we have this structure, how we realize this structure, and what is the problems associated with this structure, because you already seen that one point that this transistor structure which we have, bipolar transistor NPN structure, is different from the conventional BJT structure, where you have the emitter on top and collector on the bottom, okay. Here the collector is on top and emitter is on bottom. So, this also this gives rise to certain problems, okay. So, we shall see the step by step how this is fabricated, okay, and some associated points about this, okay. So, first what you do is in order to fabricate this I squared L cell, you start off with a n on n plus substrate. Okay. Of course, this is not to scale. Okay. Usually, this n plus substrate consists of the entire. I mean, if this is very thick. Okay. I have just drawn it because of convenience of, because I have to draw a lot of things in this n region. Okay. This n region may be about 5 microns thick. Okay. Whereas this may be around, depends on the wafer which you are using, maybe 300 or 500 microns thick. Okay. So n plus, this is mostly n plus. Okay. This is n region is grown epitaxially on top of the n plus region. All right. Okay. A few about 5 microns maybe. Okay. Why do you require a n on n plus for this fabrication? Why not a total n plus structure? Because if you go back to this structure here, in the n region, so this is the n epitaxial region. Okay. You have to diffuse and make all these junctions. Okay. Now, if you have to make a junction, okay, by diffusing p regions, so in this region the p concentration, that is the acceptor ion concentration, must be greater than the background donor concentration, okay, which means that the donor concentration must be low. All right. Otherwise, you can never make a junction. All right. So, it is necessary that you have an n on n plus wafer. Okay. Why an n plus at all? Why not a total n region? Because this n plus is actually acting as the emitter of the NPN transistor. So, you require high concentration. Okay. So, you require n plus, all right, but you cannot make it totally n plus up to the junction, because it is you have to actually fabricate this PN junctions, which is done by diffusing from the top, and so you require a lightly doped region in which you actually fabricate or diffuse these p regions. All right. So, you have to start with a n on n plus wafer. Okay. So, all right. So, that is what is the starting point. Then what you do first is you make the guard rings, you diffuse the guard rings. Okay, that is, these are n plus regions. Okay, just something like a isolation in a normal BJT process. So, I will also draw the mask drawing, that is from the top view. So, if you look at the wafer from the top, so this is the region in which you diffuse this n plus. All right. Okay, it is a ring like this. This is from the top view, this is the cross sectional view. So, you have an n plus ring in, okay, a tub sort of thing in which you fabricate this. Now, why is this n plus guard ring necessary? Okay, again I come back to this figure. Okay, it is necessary because of a few reasons. Okay, for example, you see the NPN transistor. If you look at the NPN transistor, this is the base of the NPN transistor. Okay, and this is the emitter. N region is the emitter. Now, the base current of the NPN transistor depends on how much hole is injected from the base to the emitter, okay, and that depends on the emitter concentration. You see, when there is minority carrier stored in the emitter region, okay, they recombine. Minority carrier in the emitter means holes. The holes, when they recombine, okay, to compensate for that, holes are injected from the base to the emitter. So, if there is more minority carrier stored in the emitter, in this case lightly doped emitter, okay, you have more hole current injected, okay, that is more base current, which is going to reduce the beta of the transistor. So, you have to reduce the minority carrier stored in the emitter. That you can do by increasing the doping concentration on the emitter side, okay, because if the emitter doping concentration is increased, you know, the minority carrier is proportional to Ni squared by Nd, okay. So, that is reduced. So, basically you are reducing, by making this n plus, you are reducing the holes injected into this side, okay, all right, of the emitter, okay, because you are reducing the minority carrier concentration here, okay. So, basically it is for this reason you would like to have a guard ring, because any unnecessary region, n region left here, you know, there is going to be unnecessarily some stored charge, okay, which is going to create problems. So, and here also, if why a guard ring this side also, because again if you look at this PNP transistor, okay, the useful holes are those which are injected from the emitter towards the collector. We do not want holes injected this side, because that they are not going to be of any use, all right. So again, to reduce this injection of holes on the other side, okay, you can make an N plus, okay, which means that the whole concentration here is suppressed, okay, because of, if you have an N plus here, N plus means highly doped N region, heavily large concentration of donors. So the whole concentration is going to be proportional to Ni squared by Nd. That is, already we have seen that. So basically you suppress the whole injection on this side, which is going to be a waste actually. So you make a guard ring, okay. So all the activity is confined to this region, and there is no injection of charges on these sides, which is actually going to be a waste and is going to act as is going to be a waste and reduce the performance, okay, of this circuit. Okay, so you have a guard ring like this. So you first make the guard ring, and then you do the p diffusion to make the p-n junctions. Okay, actually you should make it as deep as possible, you know, so that this region, the N region, okay, which is actually the lightly doped region, is as small as possible. Okay, the thickness of this N region is going to be as small as possible, because this we would like, because this N region, whatever is the thickness, you know, you have a lot of minority carrier stored charge here. Okay, again from the same principle, if you have a lot of minority carrier stored charge here, there will be more hole injection, okay, from the base to the emitter, okay, which is going to reduce the beta of the transistor. You know, in a p-n junction, okay, say if you have a p plus n junction, okay, it is mostly holes injected from p plus to the n, okay, because the n is lightly doped, okay, and so the minority carrier concentration is more, okay. Whereas if p plus, there is going to be very little electron from injected from electrons injected from n to p, because that is highly doped, okay, the minority carrier concentration is less. Similarly here, so if you reduce this N region, okay, you actually reduce the whole injected, because in the N plus region there is going to be very little hole concentration, okay. So if you reduce this N region, there is going to be less injection of holes into the emitter, okay, which is the base current, okay, and there is going to be the electrons injected from the emitter to the base is going to dominate, okay. So this must be made as thin as possible, okay. So if you look at so this is the cross sectional view. From the top view, the mask, okay, is going to be something like this, and this is the base. All right, so this corresponds to this region, and this is the injector, okay. In fact, sometimes a second p diffusion is done on the injector side, okay, just to increase the whole the acceptor ion concentration here, because this is going to act as the emitter of the PNP transistor. So this should have a higher concentration compared to this, but okay, you can also avoid it, all right. But this is going to act as the base, okay. So you should, you cannot increase it make it very high concentration, all right. So this is the P region, and then the next step is you diffuse the collectors in the P regions. So these are N plus, okay. So the mask, you have, this is the mask through which you diffuse the N, okay. This corresponds to these regions, okay. And then finally, so these are P, okay. And then finally what you do is you take the contacts, okay. You take a contact from here, you take a contact from here, and you take a contact from here, take a contact. So you draw it like this. This is the convention for drawing the mask layer. This is the hatched region. You have a contact here, you have a contact here. So this is the I squared L cell, this is the mask drawing. So you have an injector here, this is the injector, this is the input or the base, it's also sometimes called the base contact. This is the collector C1, I write C2, these are two collectors here, all right. So this is the mask drawing, okay, all right, or the top view, and this is the cross sectional view. So this is how you fabricate the I squared L cell, all right. This is very important because we shall be coming back to this again, mask drawings. We shall look at mask drawings for more complicated circuits, okay. Okay, so this is how it looks like, right, from the top, okay, all right. Okay. Now with that we move on to more general circuits, that is we have now discussed, we have now seen an I squared L cell, okay, that is a NPN and PNP combination here, okay, that is the I squared L cell, okay. Now of course what our interest would be to see how you can make, for example, NOR gates or NAND gates, okay, because that is going to act as the basic structure, okay, around which you make more complicated circuits, okay. So that is the next step. Should remove this. Okay. Now, so you shall see now that when I am drawing more complicated circuits, okay, I am actually repeating the I squared L cell, okay, basic cell is being repeated, okay, many number of times, okay. So these are two cells, I join them here, okay, again another cell I draw here, okay, and I connect all the injector points together, short them, okay, and then you can have a connection to VCC through a resistance. So usually, as I said, okay, this resistance which you have here is usually external to the chip, okay, you don't require a resistance inside. So if this is an I squared L circuit, okay, you don't require a resistance as such, okay. So if this point is made available, you can connect through VCC through a resistance. So that is the one advantage of I squared L, okay, you don't require any passive components, okay, and also this structure is a merged structure, so you require very little area, okay. So as I said that I squared L is more suitable for large scale integration amongst the different bipolar logic families, okay. Now suppose I have the inputs A and B here for this circuit, and the output, say this point is F, okay. So A and B are the inputs and output is F here, okay. I'll call this F1, all right. Now what is the logic that you achieve here, okay. So if you draw the truth table, if I, okay, AB F1, say 0 0 0 1 1 0 1 1, these are the four combinations, okay. Now when A and B is 0 0, that is these 2 points are low, okay. In I squared L, when we say these points are low, I mean that means basically you have a saturated transistor connected here, all right, that is the output is low. Now what is going to happen, what is the state of these transistors? They are both going to be cut off because these inputs are low, okay. So these transistors are cut off. Then when this transistor is cut off, what happens to this current in this current source here? It flows into this base of this next transistor. This voltage here is going to be around 0.7 volts, okay, and this output is going to be high. So that is, here we refer to high as the base emitter drop of a transistor, okay, that is around 0.7 volts, and low will be around 0.2 volts, which is the voltage when a particular transistor is saturated. Okay. So, that is the range 0.2 to 0.7. Okay. The voltage at all nodes lie within that range, okay, in this circuit. So, when it is 0 0, it is 1. Okay. When one of them is 0 and the other is 1, what happens? So, suppose this is 0 here, okay, A is 0, B is 1. Okay. This transistor is cut off. Okay. What happens to this transistor? 1 means here there is a cut off transistor which is cut off. So, this current source, the current from this transistor flows into the base. This transistor goes to saturation, okay, and when this transistor goes to saturation, this voltage here is pulled low, okay, because this current source, okay, this current will flow into the collector of this transistor, and here this transistor is not going to get any current. Okay. So, this point is going to go low, this transistor goes to saturation. So, similarly 1 0 also you have the same case, and when it is 1 1, both the transistors are conducting. Okay. The same situation, this point goes to low because this voltage here is going to become low, because both these transistors are in saturation. So, the output is going to be low. So, what is the logic here? NOR. Okay. So, this is a NOR function. So, f is equal to a NOR function of A and B. All right. Okay. Now, let us look at it in a different way. Okay. Suppose I have another circuit here, say another transistor here, another cell basically, okay, and suppose I look at the logic values at these points. Suppose I call these points, you know, I call this x, I call this y, okay, and suppose I call this f2. Okay. That is, x is the logic is the value at the collector of this transistor, okay, and y is the at the collector of this transistor, okay, and f2. That is, if this transistor is in saturation, okay, we shall say x is low, okay, and if this transistor is cut off, we say x is high, okay. All right. Okay. Of course, you must be a little bit wary about this, that actually you see these 2 points are shorted here. Okay. So, how can one be high and one be low? Okay. The definition here is slightly more tricky, in the sense that here what you are saying is when we say high and low, it refers to the state of this transistor. Okay. That is, if this transistor is cut off, we say x is high. If this transistor is saturation, we say x is low. Okay. So, if you define it that way, okay, and we write another truth table, okay. So, what is the logic here? Again, f2 here, you know, it is high if this transistor is cut off, and low if this transistor is saturation. Okay. Then if 0 0 means both the transistors are in saturation. So, this current flows here. So, this transistor is cut off. So, this is 1. Okay. Now, if one of them is 0 and the other is 1, that is, one of them in saturation and the other in cutoff. Okay. Saturation means the current is going to flow this way. Okay. This output transistor here is going to be cut off. So, what is the output going to be? Right. All right. And when both of them are cut off, then only this current flows into the base here, all right, and when it flows into the base, this transistor goes to saturation, okay, and the output is low. Okay. So what is the logic here? It is NAND. Okay. So you see that with this particular circuit, okay, basically what we have done is we have taken some I squared L cells and we have just connected wired the outputs, okay, the collectors of these, okay, and we have achieved some logic. Okay. You can achieve either NOR logic or NAND logic. Okay. For NOR logic, the inputs are considered at the base of a transistor and the outputs are also at the base, okay, of the next transistor. All right. Okay. Whether the input base voltage is high or low, that is what we are considering. Okay. From base to base, okay, it is NOR logic. Okay. All right. So if we are considering whether the base voltage is high or low at the base of a transistor, okay, and if you consider at the collectors, okay, that is whether the transistor is in saturation or cutoff, okay, all right, then it gives a NAND logic. Okay, from collectors to collector to the next collector, okay, it is a NAND logic. Okay, so you can consider it in both ways. Okay, the idea is that basically what you have to do is, in order to obtain, you have to realize a circuit. You have a given circuit which is drawn in using NAND gates, or okay, then you should be able to go to this circuit. You should be able to draw the transistor circuit. We shall come to that, okay, subsequently. That is, given a NAND circuit drawn using NAND gates, you should be able to draw this transistor level circuit for I squared L. And once, of course, you have this circuit, you can go back to the layout, okay, and you can do the design. Okay, or even if you have a NOR circuit, you can do the same process. Okay, go to the transistor level, okay, and from there you can, how a cell looks like, okay, from cross section, and then you can go to the layout. All right. So that is what we shall do subsequently. Okay. So again, just to repeat, from base to base it is NOR, from collector to collector it is NAND. Okay. Okay. All right. Before we go ahead and do that, that is just from a NOR level to or a NOR circuit or NAND circuit to the transistor level, how you obtain that. Just one point I would like to make is, okay, that we have been talking of these multi-collector transistors, okay, these NPN transistors having multiple collectors. Okay. Now, why do you require multiple collectors? Is it necessary? Okay. Yeah. So the question is, suppose you want to do obtain a NOR of, you want this f is equal to, you want to realize these functions, say, that is NOR of A and B and NOR of A and C. Okay. Now, how do you do that? You have again A, B, the two inputs, all right. You just short them. Okay. Of course, it is going to the base of some other cell. Okay. So I am just drawing the, I am not drawn the PNP, I am just drawing them as current sources here. Okay. All right. So here you will get NOR of A and B. Okay. Now, if you want to have a NOR of A and C, what do? You have a C input. Okay. Now, suppose you want to do it like this. Okay. If you don't have multiple collectors, okay, you take this point itself, you connect it here. Okay. Now, do you have a NOR of A and B, C here? That is the question. What you have here, what do you have here? Because you have shorted, you see at this point you have shorted A, B and C. Okay. So, basically what you get at this point is NOR of A, B and C, not A and C. Okay. Because basically at this node A, the outputs of all the three collectors are shorted. Okay. So, here also you get NOR of A, B and C instead of just A and C. Okay. So, now, so that is the problem. Okay. You have basically shorted all the 3 collectors. Okay. So, you have a 3 input NOR gate, all right. So, what you have to do is you have to have a multiple collector like this and coming here like this. Okay. So, in that case here you have shorted the collector of these 2 transistors whose at the inputs you have A and B. So, this is NOR of A and B. So, here at this point you have just shorted these 2, okay. At the inputs you have A and C. So, this is going to be NOR of A and C. Okay. So, using multiple collectors, okay, I mean if you want to have logic functions made derived out using the same inputs, okay, you just require multiple collectors, okay, all right. So, that is also an advantage of I squared L, okay. Using multiple collectors, okay, it improves your functionality in the sense that you can have more logic functions derived, okay, using less circuitry. Okay. So, this is the reason why you require multiple collectors. Okay. Okay. Now, what we shall do is next, as I said, we shall try to take a circuit, okay, a simple circuit drawn using NOR gates and try to see how you can realize the equivalent I squared L transistor circuit. Okay. All right. Now, let us take this circuit. Can you say what this circuit is? This is the, so you have, here you have NOR of A and B. Okay. Here you have the NOR of complement of A and B, and then again you are following it up with a NOR. So, what you have here is, well, this is the circuit of is a half adder circuit basically, all right. So, here you have the sum and here you have the carry. Okay. That is, if you have here you have A bar and B bar, all right. And if you take the NOR of A bar and B bar, okay, you have here AB. Okay, this is AB, all right, and here you have actually A bar B bar, isn't it? Okay, so this is you get the exclusive OR. Okay, so this is A exclusive OR B. So, this is the sum output and this is the carry output. Okay, so, this is the half adder circuit, all right, a famous circuit. Okay. All right. Now, let us try to realize it using I squared L. Okay. Now, I shall just note down some points, okay, how you should go ahead with converting this into I squared L. So, first, I think if you follow this point by point, it's very easy. Assign a number to each gate. Okay, so you call this say gate 1, this 2, 3, 4, 5. Okay. Number of inputs So, okay, sorry, I think each gate output is represented by a node. See, by a node what we mean is, in the I squared L circuit, okay, when two collectors, you are just connecting two collectors, okay, that is a node. All right. Basically, the logic is being achieved by connecting the collectors of each individual cell. Okay. So, each gate output here is represented by a node in the actual circuit. Okay. Number 3, number of inputs to the gate is equal to number of collectors at the node. Okay. That is, if you have a 2 input gate here, you will have 2 collectors connected at the node. Okay. Of course, you do not have 3 input NOR gates. If you have 3 input NOR gates, you will be basically tying up 3 collectors at that particular node. Okay. All right. And number of fan outs equals number of collectors of the next transistor. Next transistor means the node is at the base of a transistor. Okay. The node is at the base of a transistor. Okay. So, the number of collectors for that transistor at whose base you have the node, it denotes the number of fan outs. For example, if you of course, this is a very simple circuit. Okay. It depends on if you have more than one fan out. Suppose at this point, this is going to somewhere else, okay, some other circuit. So, here you are connecting this output to 2 points. Okay. So, the number of collectors, okay, it has to be the next transistor has to have 2 collectors, because the output of this gate is going to be fed to 2 different points. Okay. And you cannot use the same collector to feed it to 2 different points. Okay. Just as we had seen in the example where you are making A plus B and A plus C. Okay. That is, if A has to be fed to 2 points, okay, you require 2 collectors for that transistor. Okay. So, if you have more, the number of fan outs for this gate is more than 1, okay, you require more number of collectors. Okay. So, this is the general rules you have to follow. Once you follow this set of rules, you can very easily obtain the circuit. Okay. Now, let us look at this, how to realize this circuit. Okay. First, we shall see here A and B. Okay. All right, A and B, okay, they are tied together. Okay, this is one node, okay, and this node represents gate 1. Okay. All right. So, gate 1, this output is represented by this node at this one. All right. Now, the next gate is number 2 is a inverter. Inverter, of course, you can consider it as a 1 input gate. All right. So, basically the node is, there is just one connection. Okay. There is actually not a node, but all right. And so, you have a connection coming from A. So, like this. So, this is 2. Okay. All right. So, you can, if you go back to this circuit, you will again see that from point A, we are actually taking two connections, okay, all right. So, you require for this that particular transistor, it must have two collectors, okay. Similarly, for gate 3, all right. So, this is the node 3, okay. Now, what about gate 4? It is a NOR gate. Again, the inputs are 2 and 3, all right. So, this is 4, all right. Okay. And then that leaves us with 5, where the inputs are from 1 and 4, okay. So, this is 1, 4, and this is so this is gate 5, okay. So, that completes the circuit, all right. So, that particular circuit can be represented by this layout. Of course, here one thing is that we have not drawn the PNPs, we have just drawn the NPNs. Usually, you will many cases you will find that in also in textbooks that the PNPs are not drawn, okay, because it is always assumed that at each base, okay, you have a PNP. Okay. So, that is common. So, you need not draw it, okay. You can just write separately that at each base it is assumed that there is a PNP, okay, at injector, all right. So, many cases people just avoid drawing it, okay, but it is assumed it is there, okay, because otherwise it becomes circuit looks very cumbersome, okay. So, that completes the circuitry. Of course, if you have to take if you take want to take outputs, this point, this 5, the point 4s and 5, okay, are the where you have the carry and the some logics values. But suppose you want to take an output directly from those points, what do? You can put a resistance here, okay, and connect it to supply, okay. Okay. So, this point will give you the sum value, okay. That is, when any of these transistor goes to saturation, okay, the voltage here is going to be 0.2 volts, because there is a current flowing here and the voltage will drop to 0.2 volts, and if both of them are cut off, the output is going to high, okay. You can put that. Now, if you want to take the carry input, what do? The carry output, what do? You must take the output from this point. Actually, it is 4, you know. So, basically what you do is you cannot take the output from here, okay, because this voltage cannot rise to more than 0.7 volts, okay. So, what do? What you can do is, again, you require you have to make another NOR gate, okay, and do that. That is, basically you can take another collector here and connect it here, all right. Now, what is the logic here? It is the same as 4, okay, but here you can connect resistance to VCC. Okay, so, this is going to give you the carry output A. All right. So, if this transistor goes to saturation, this voltage is going to go low. In any of these transistor goes to saturation, this voltage is going to go low, and both of them are cut off, then only this output is going to be high. All right. So, if you want to take an external connection, okay, you have to do it this way. Okay, it is very simple. You do not require any additional transistors as such. You have to just require additional collectors for this. Okay. All right. So, Okay. Now, yeah, so you see that the advantage of I squared L, okay, is very much glaring here, that you have made a half adder, a complete half adder, which requires 5 gates, okay, or here, 1, 2, 3, 4, 5, and you just required 6 transistors. Okay. Whereas in TTL, for example, okay, just one single gate you required so many transistors. All right. So, this just 6 transistors you have required a half adder. Okay. So, you can look at the savings in area, okay, when compared to TTL. Okay. I mean, it's really great. Okay. So, that is what made I squared L so much when it was first invented. Okay. It became so popular, okay, that you can really make very large scale circuits. Okay. And also you don't really require any resistance or any passive components. You can just connect the transistors like this, okay, and achieve the results. Okay. All right. Now, from here, once you get this circuit, okay, the next step, okay, is finally you have to go to the layout. Okay. And once you have the layout, one can really fabricate it. Okay. You have the mass drawing. Okay. You generate the mass, that is the regions where you want to diffuse different regions, okay, and then you can go for the mass drawing. So, the next step is the layout, which is very simple actually. So, this injector, see, what we have seen is one cell. Okay. Now, you have so many cells to be connected. Okay. Now, if you look at each transistor now, say for example, you have we shall call this, say you have one transistor here with inputs with input A. Okay. So, this is a transistor with 2 collectors. This transistor with input B, this is also a transistor with 2 collectors. Okay. So, you can draw it like this. So, this is the base, these are the 2 collectors. Okay. So, this is the base, these are the 2 collectors. All right. And then what you do is you short these two, one of the collectors. So, the one input is A and the other is B. All right. And then you short one of them and it goes to the base of another transistor here. Okay. So, what you do is, and that particular transistor has just one collector. So, it goes, you draw the base like this and this is the collector. So, you short them. So, this is the metal line running, just short this up. Okay. So, this is how you make connections, all right, and you can actually sort of draw the layout of the entire circuit. Okay. I will leave it to you. Okay. You can try it out, all right, and maybe next class I will draw the circuit for you. I mean, I will give you an opportunity to try to draw out the entire circuit. Okay. So, the main point is this is the injector and you can have circuits on either sides of the injector. Okay. So, injector will be injecting on both sides. Okay. So, anyway, I will leave it to you, please try it, okay, and in the next class I will draw it for you. Okay, we will stop here.